record and share the screen. Okay, we are back to business. So this is it, example number 13. It's a rather comprehensive example that you will see from the design and everything, okay? So we have the case where we have the 1.8 meters long beam, which is rather short if you, consider the typical beam length. We have the date load of 6 ton per meter and live load 9 ton per meter. That means the load acting on the beam has already been calculated. And we also have the architectural requirements saying that the depth of your beam cannot exceed 250 millimeters. And we also have the condition where the deflection due to live load should not exceed L over 360. You're going to use SM400 steel, and the concrete, which is the support here, is made of the strength 240 kilogram per square meter. Okay, so let's say, because this example was done a long time ago, and I took it from my class a little bit, so it was done by the LRFD method. Okay, if I don't say anything, when you do your project, you should always use the ASD, okay, because that would be in good accordance with the Building Act that we have. All right, so let's say we begin by, considering the load combination. And in LRFD, we generally have 1.4 dead load or 1.2 plus 1.6 live load. And if it's not something extremely unusual, this case will always govern. And so after the calculation, I got 21.6 ton per meter. Remember, this is the factored load. Or you can say WU, okay? So without further ado, I can go on and calculate the shear and the bending moment. So that becomes a value that we will need to look at when we design. And this beam is, let's say it is laterally braced by the floor. So you can say it's laterally braced. So that means your MN is going to be equal to MP, right? As usual. And we begin the design by assume that we are going to have the compact section. And from this MP, which is equal to Fy multiplied by plastic section modulus, and then multiplied by the phi, okay? That becomes your, no, I shouldn't apply, I should multiply by the phi, because that would be nominal moment, okay? That would be the design moment, and we have the phi mn, which is equal to phi mp. It should be greater than mu. So with that, we can calculate the required plastic section modulus, okay? And we have the moment from the load 21.6 multiplied by the length WL square over 8. So it's 8.75 ton meter. That is our target. So if I derive it from here, I will have the plastic section modulus. Can I write bigger? Oops. Plastic section modulus must be greater than the value of mu divided by phi, right? You see, phi will divide mu so that it increase the value. And of course, this is divided by Fy as well. So that's your mu. And we change the unit a little bit because that's in ton meter. So multiply by 1,000 and multiply by another 100 to make it into kilogram centimeter. divided by phi and then divided by Fy. So I got the Zx that I need to look at is 389. I should pick any section that has a greater plastic section modulus than this. Okay, now I try this section. It's 250 by 125 by 44.1 kilogram per meter. And you can pick this value from the table right away. If you haven't, I can just show to you that, okay, right here, 250, and this is the one that we are doing today. Okay. This is the one. Okay, so you can pick this up. That's the BF over 2TF, and then H over TW is 27.1, and we're going to use K in our design as well, so you might as well remember that it is equal to 27 millimeters. Okay, so with that, we are going back to our design examples. Okay, so that's our BF over 2TF and H over 2TW. So this value is lower than the limit. Oh, what is this? Which is, remember, if you could recall, this is 0.38 square root E over Fy, and this is 3.76 square root E over Fy, you know. So both flange and web are compact, and we can say we have compact section. And you see sometimes my example, you can just pick this number up from my table as well, because I now remember that you guys got this table from me. So you can just use the typical table, this one, you know, pick the plastic section modulus here, and multiply by Fy, multiply by phi yourself, or you can just use this table as well. This is SM 400. Now I have everything available for you, but for some reason, because during the development, they want the universal unit. And the thing is that the universal unit, kilogram, is not a unit for force. But some countries use it extensively. That's why they have to call it kilogram force, you know? Kilogram force as a unit. And I'm kind of used to this unit as well. But this table, it was developed by using a Newton meter. So we need to do some unit calibration before we could use it. So, if you want to do so, you can just pick up the phi mn from this table right away. That's the number. Okay, either way, it's fine. But you need to change the unit if you want to use this table. Oops, sorry, it's a accident. So right here, say because the section is compact, so we can just pick up the number and calculate right away. Okay. So here we are. The phi mn is 12.5 ton meter, which is greater than mu. So we have the big OK. So the flexure is done. Now it's time to check the shear. The ratio of the web is H over TW is the same as that, but the limit is different. This limit is for the shear. It is 2.45 square root E over Fy, but still this is less than that. So you say CV is equal to 1, and you can calculate the shear strength of the member by using 0.6 Fy multiplied by depth multiplied by the thickness of the web, or you can just pick the number from that table as well. And now we have the section. We can check the deflection, and our limitation is L over 360. but it's a deflection due to the live load alone. So I only bring the live load. And remember, this is a good example to serve you that even though you design as the LFD, when you check the deflection, it is always a service load. Deflection, oops. Deflection check is always service. Okay, now I forgot to correct this. You know, this is power. Okay, 3, this is power, and maybe I should use a different color so that you know. This is power. Okay, and that's how I handle my calculation of the deflection. I multiply the load with the meter, and then I have L cube left, and I use it in centimeter. So I take care of the unit change, and I got 0.1 centimeter, which is less than our limit of L over 360, which is 0.5 centimeter. So I am okay in terms of deflection as well. Now I can move on to the base plate. Okay. Now, generally, when you have to design for this, you know, you don't have the number, but I sort of did everything I had, so I would know, okay, I should begin with this. So the width of the plate, you should know that this is the front view, so that you see the beam looks like this. This is a side view, and the size of the plate from side view tells you how much N you can use, okay? And let's say I didn't have the calculation to show you, but this can be done by using the formula. But because this base plate is at the end of the beam, so you would want to use the 2.5K plus N formula multiplied by T web and then multiply by Fy, and the phi is equal to 1. Divide by 1000. That's the number that you're going to get. K here is 2.7. Remember, we look at it, and N here is 10. Okay, and web crippling, you need to check your N over D ratio to pick the formula. And N is now 10, D is 25, right? So it is roughly 0.4, and 0.4 you're going to use the formula that for N over D greater than 0.2. Okay, now let's take a look at the concrete crushing. Now let's say, because my beam size is 175 by 250, okay, so I pick the plate that is slightly wider than the beam itself, because right here the beam is 175, so I can put the beam on the plate without any problem. So my N is sorry, my plate size 200 by 100 millimeter, and the area A1 is 20 by 10, so it is 200 square centimeter. And now the area A2, it's sort of given somewhere before, but sorry, I didn't include it in here, but let me take a look at my note quickly. Excuse me. This should be the one, but I cannot seem to find the okay, I think somewhere I forgot to include this, my apologies. But I think this beam, this steel beam, sits on the concrete beam, and the situation is this. Okay, so let me go to this node and try to give you a proper picture. So let's say we have the concrete beam in this direction. Okay, and the steel beam sort of coming in this direction. And so, right, this is the beam with the width equal to 17.5. So I am using the plate that is 20 centimeters wide. Okay, so that's my plate. And the size of the plate here, that's 20. And remember, I have the n that is equal to 10. Okay, so that's the size of the plate. And I believe that the beam width here is given as 25 centimeters. Okay, so that means you can see that you sort of have the room left here for 15 centimeters, or you can say it is 7.5 centimeters on each side. Correct? So if you have 7.5 to go in the vertical direction, because of the one-to-one slope, if you can go up 7.5, you should go sideways 7.5 as well. This is 7.5 as well. All right. 7.5 and 7.5. Okay. So that means the area A2 would become 25 here, which is already limited by the width of the concrete beam. And then this is equal to 20 plus 2 of 7.5 or 35. Okay. Now back to, is there anyone has any question with this? Remember again that this is the size of our steel plate. Okay, 20 by 10, and this steel beam coming in this direction and placed on the concrete beam that is, say, perpendicular to the steel beam, which is in this direction. So let's say if you look at the plan without the dimension, you would see, you know, this is the concrete beam and the steel beam coming in like this. Okay, and the width of the concrete beam is 25 centimeters. So with that, we can sort out our A2. A1 is of course 20 by 10. And A2, because the concrete is 25 centimeters wide, so we can just go on the side by 7.5, because if it's 25, the width of the steel plate here is 10, so that leaves 75 on top and at the bottom. So you can go 7.5 on both sides as well. So you have 2 of 7.5, you multiply, you add that with 20, so that's why we have 35. So A2 becomes 25 by 35. Okay. So let's go back to our document here. So that's why we have A2 here equal to 25 by 35, but you need to be careful here, because after this, you already know this is 200, and 4 multiplied by 200, it's 800. So no question, this A2 is beyond the limit. Okay, So back to the formula. That's why it's the phi multiplied by 0.85 FC prime A1, and then that square root term of A2 over A1, you know, it becomes 4 because you cannot go, 2, sorry, 2, because you cannot go beyond that limit. Okay, and then after the calculation, it's 49 tons, so it's, woohoo, we are safe. Okay, so after we got the size of the blade, now it's time to calculate the FP. The load is, now, you know, there's another mistake that many students can make is that you will not use the actual load here. Remember, after the calculation, that this is the load that your beam has to carry. That is the load. So when you design the structure, you use this load. You don't use this. You don't use this capacity to design the base plate. You use the actual load. Okay, and that is the size of the plate. So FP is now the actual load, the actual ultimate load, okay? The actual factored load divided by the area of the plate. So we have this. Okay, that becomes your FP. And now, because this is the beam model, I can go back and look at the beam. If this is 20 centimeters wide right here, the end distance that I am going to use to calculate the moment on the plate will be half of this minus K, right? So it is where? Oh, here. Half of 20 is 20 divided by 2, and K, we sort of look at the table, it is equal to 27 millimeters or 2.7 centimeters. So your N is 7.3. So your moment becomes, you know, WL square over 2. Your W is 97.2. Your L is 7.3 square over 2. That's how you get moment. And this term should not be more than phi and then MP of the plate, which is Fy Zx. And Z is, you know, B is equal to 1 because we design on the strip of 1, and then it becomes a D square over 4 or TP square over 4. Okay, you can solve that and you get the plate thickness. And again, try this kind of thickness should not be available anywhere, and generally the plate available in the market it's in the increment of 3 millimeters. Increment of 3. So you can easily find the plate that 3 millimeters thick, and then 6, 9, 12, and so on, until it becomes like 18, and then the 20 millimeters, and then 25. Okay, so sometimes to go to, like, you wanna use the most practical size and save money. So you would say, hey, can I use a 22 millimeter plate? You better check the availability of the market as well, because sometimes when you assign the size of the plate and they cannot buy it anywhere, you know, they're gonna have to change it in the end anyway. Okay, so that's it. One example. Is there any question? So if there isn't any question, let's move on to another example, but this time it's the column base plate. Okay, so, you know, let's say per your project, by now you should know how much your column how much load your column carries, right? So you can always design the base plate and on the ground level, okay? After you know the size of your column. So be practical and use plate slightly larger than the column footprint, okay? You know, the column footprint would basically, it's just this, okay? So your plate has to be bigger so that, you know, they can weld the base plate to the column, all right? So let's say if you know the load, it's time for you to design the proper size of the plate and then the abutment, okay? So let's say, wow, in this case, it's very low concrete strength. It's like, you know, it's done by hand. And in this case, let's say we have a very, very large concrete foundation or abutment. So that in this case, it is assumed that A2 over A1 is greater than 4. So that means in the calculation, we can use this equal to 2 right away. But that is not always the case, you know. So let's say in this case, we know that our ultimate load, again, this is the example based on LRFD. Because once you see the U, that's the ultimate load or the factored load, you should know that you must design this by using LRFD. So because we know that the area of the concrete is extremely big, so you can assume that the factor is 2 right away. By doing this, you can calculate for the area of the plate A1. All right. You can play around if you don't know that the concrete will have to be very, very large. Okay. And so by this, however, we know that the situation gives us the very large concrete, so we can use 2 right away. And therefore, we just sort of set up the concrete crushing strength to be greater than the PU. And we can calculate for the area A1 now. That's going to be PU divided by phi multiplied by 0.85, FC prime, and then 2, which is a factor. So I got the area now. That the A1 has to be greater than this. But now it is an art of design. Okay. So you have the size of the column, and then you have the area that you need. So we can now plug in this equation. Remember that the model says the green area is your rigid zone. So to determine the M and N distance, you sort of put this area, you know, this whole area into your consideration. So the N is 2M plus this, and the B is 2N plus this. So that's your area equation. So you see, actually it becomes the, you know, one equation but two unknowns. So I can say set up M equal to N first to optimize my situation, so to speak. So I solved this and I got M equal to N equal to 5.5. So I can bring this back and, you know, no, that's not where it should go. And say here, oops, oh, geez. I should always turn this off first, right? And then do this. I can use this, plug in this equation. Okay, and then I got the size of the plate out of this. It may not be a round number, but then in the end, when you start doing it, you may want to use the round number like that. And then come here and try to calculate the actual M and N distance again. Okay. Now this may not be the very good example. It's okay, you know, but it may not be practical because you can notice that the width and the depth or B and N distance, they are quite different. Anyway, so after you pick the size, you come back and calculate the true length of M and N. And now you see that, okay, this is larger, so it becomes the case that governs your design. And now you know the size of the plate, so you can also calculate your FP as well. So your FP is equal to the load P divided by BN, the size of the plate that you use, which is right here. So you got your FP, or the area is this one, okay? So you got your FP, and then you can use the governing distance, which is this one, to calculate the thickness of the plate from the formula. And there we go, 2.26. So I go with the typical plate thickness, 25 millimeters. So it's 315 by 350 by 25. So that's it. That's the end of the design of the base plate. Okay, is there any question? Pretty quick because we have the documents ready. Folks, so if there isn't any immediate question, let me stop the share and stop the record.